Welcome to our lecture on the binomial option pricing model. Imagine you are a hiker standing at a fork in a trail where you can only choose to go up the mountain or down into the valley. There is no middle path. Today, we will see how this simple idea of two distinct paths allows us to price complex financial derivatives with absolute mathematical certainty. Let us begin. Now that we have introduced the topic, let us understand the core framework. Why does this concept matter? Financial markets are incredibly complex and continuous, making them hard to predict. The binomial model simplifies this by breaking time into discrete, specific periods. In each period, we assume the stock price will only do one of two things: increase by a specific factor or decrease by a specific factor. By mapping out all these possible up and down paths, we create a branching tree of future prices. This allows us to break a highly unpredictable financial future into a simple, manageable series of steps. Building on this idea of up and down movements, we introduce the most crucial concept, the risk-free portfolio. To find an option's fair price, we mathematically combine a certain number of stock shares with the option itself. We balance them so perfectly that no matter whether the stock goes up or down, our portfolio's value remains exactly the same. Because this portfolio has absolutely zero risk, it must earn the exact same return as a safe bank deposit. This relies on the no arbitrage principle, which states that you cannot make a guaranteed risk-free profit without investing your own money. With the concept of a risk-free portfolio in mind, let us look at the mathematical formula it produces. This equation calculates the expected future value of the option and then discounts it back to today. The symbol F represents the fair price of the option today. The term e to the power of negative r times t is the discount factor, bringing future money back to present value using the risk-free rate r and time t. The symbols f subscript u and f subscript d are the future option payouts. If the risk-free rate increases, the present value factor changes, directly impacting the option's price. This formula we just saw leads us to an important question. How do we weight those future payouts? We use the risk-neutral probability, denoted by P. It is important to understand that this is not the actual real-world probability that the stock will go up. Instead, it is a mathematical probability that makes the expected return of the stock exactly equal to the risk-free interest rate. The term e to the power of r times t is the growth factor of a risk-free investment. The symbols U and D represent the up and down multipliers. As the risk-free rate increases, this probability P increases, which generally makes call options more expensive. Before we move on to calculations, let us visualize this framework. Here you are looking at a one-step binomial tree diagram. On the left, we have our single starting point, representing the current stock price S and option price F. From here, time moves forward, branching into two possible futures. Following the upper path with probability P, we reach the optimistic scenario, where the stock price is S times U. Following the lower path with probability 1 minus P, we reach the pessimistic scenario, where the stock price is S times D. By calculating the values at the end of these branches, we can work backward to find the value at the start. Now that we have our formulas and visual map, let us see this with a concrete example. Suppose a stock is currently priced at 20. In 3 months, it will either increase by 10% or decrease by 10%. We want to find the price of a European call option with a strike price of 21. First, we calculate the future stock prices. We multiply the current price of 20 by the up factor of 1.10 to get 22. This is our best case scenario. Then, we multiply 20 by the down factor of 0.90 to get 18, setting the lower boundary for our tree. Having found our future stock prices, we must now determine what the call option is worth in both scenarios. A call option gives us the right to buy the stock at the strike price of 21. In the up state, the stock is worth 22. We can buy it for 21, making a profit of 1. So the option is worth 1. In the down state, the stock is worth 18. We would not force ourselves to buy an 18 stock for 21, so we simply let the option expire unused. The option is worthless here, so its value is 0. With our future payouts established, we calculate the risk-neutral probability. Using a risk-free rate of 12% and a time of 0.25 years, we plug our values into the probability formula, yielding 0.6523. This means the mathematical odds favor the upstate. Finally, we use the main binomial formula. We discount the expected future value back to today. The fair price of this call option today is 0.633. Physically, this means an investor should pay exactly 63.3 cents for this contract today to avoid any arbitrage opportunities. Now that we have successfully used this formula, let us understand where it comes from. We start by building a portfolio consisting of delta shares of the stock and one short position in the option. We want to choose delta so that the portfolio's value is identical whether the stock goes up or down. We set the upstate portfolio value equal to the downstate portfolio value. By solving this algebraic equation for delta, we find exactly how many shares we need to buy for every option we sell to eliminate all risk. This delta is often called the hedge ratio. Because our hedged portfolio has zero risk, we can apply the no arbitrage principle. Its present value must simply be its future guaranteed value discounted by the risk-free interest rate. We set the initial cost of setting up our portfolio, grown by the continuous risk-free rate, equal to the guaranteed future value in the upstate. By substituting our formula for delta into this equation and rearranging to solve for the option price F, we isolate the exact price we should charge today. This gives us the final pricing formula, proving that the option price is simply the discounted expected value under risk-neutral probabilities. So we have proven that the one-step formula holds. This brings us to a slightly harder example, a two-step binomial tree for a put option. Suppose the current stock price is 50, the strike price is 52, and each step is 1 year. The stock can go up by 20% or down by 20%. First, we find the stock prices at the very end of year 2. The stock can go up twice to reach 72. It can go up, then down, or down then up to reach 48. Or it can go down twice to reach 32. Having mapped the final stock prices, we calculate the value of the put option at these 3 final nodes. A put option gives the right to sell at 52. In the double up state, selling a 72 stock for 52 is a loss, so the option is worthless at 0. In the middle state, selling a 48 stock for 52 yields a profit of 4. In the double down state, selling a 32 stock for 52 yields a massive profit of 20. Next, using our 5% risk-free rate, we calculate the risk-neutral probability for a single step, which comes out to 0.6283. With the final payouts and probability in hand, we work backward from the end of the tree to the beginning. We calculate the intermediate option values at year 1. For the upper node, we weight the year 2 payouts of 0 and 4 by our probabilities and discount back 1 year to get 1.414. For the lower node, we weight the payouts of 4 and 20, discounting back to get 9.462. Notice how much higher this is because a put option gains value when the stock drops. Finally, we step back to year 0 to find the price today. We use the year 1 intermediate values we just calculated. We weight them using the exact same risk-neutral probability and discount this expected value back by 1 more year. This completes our backward induction process. The fair price of this 2-year put option today is 4.19. By breaking a complex 2-year problem into 2 simple 1-year steps, we successfully calculated the exact value of the contract today. This step-by-step backward calculation we just performed reveals the true power of the binomial model. Its incredible flexibility. While other formulas, like the famous Black-Scholes model, only work for European options that are exercised at the very end of their life, the binomial tree can handle American options. An American option can be exercised at any time before it expires. By building a tree with many small steps, a computer can check at every single node whether it is more profitable to hold the option or exercise it early. This makes it the standard tool used by banks worldwide. To wrap up our lecture, let us review the key takeaways. The binomial option pricing model values an option by constructing a tree of possible future stock prices, assuming only up or down movements. By building a risk-free portfolio, we determine the exact mathematical probability of each path. Working backward from the final payouts to the present day gives us the fair, no arbitrage price of the option. You have now mastered one of the most robust and flexible tools in all of mathematical finance. Excellent work today.